Oh, yeah, that's going to happen. It's going to go sour. He's going to rejoin the
All right. Good morning. Today we're going to do something really different. We looked at it starting yesterday, but I want to make sure that you get these points because there is nothing that we're going to talk about today that you aren't able to do. We just have to make sure that we're interpreting some of these things, okay? So, we're going to talk today about mass spectroscopy and photoelectron spectroscopy. It is just basically interpretation of information that you already know. All today is about is making sure that you understand how to interpret some different ways of how chemists and scientists get data. Okay? So it's big deal. So a mass spectrum. What do you think that's based off of? Mass. Okay, so you're trying to deal with mass. What a mass spectroscopy is all about is that it sends an element, let's say, you take an element through this machine and through magnets and it causes it to vaporize and it turns into basically ions, and those ions have different masses. And the heavier it is, they'll fall out at different spots. If they're lighter, they fall out at different areas as they go, and then you can map out the weight of each of those particles or parts of that element based on mass. Okay? The higher the peak, the more present. It says relative abundance. Okay? So this is where we get to isotopes as well. The masses on the periodic table are average atomic masses. Okay? Oops, I need to do this, don't I? We're at 4.
It rips off the one.
Sorry, distraction. So those are averages. So what we're going to do here, and of course I don't have this plugged in, is that you have to look at what data is given to you. So it's multiple choice. So what if I told you that these are the masses of all sorts of different isotopes? What do you think it's closest to? An isotope is an atom with the same protons, so it's the same element, but with different neutrons, so it has a different mass. So if I just asked you in general, what do you think the average is? What do you think it's close to right here? Again, it's about abundance as well. It's got to be above 90, right, and below 96. That's the first concept, right? And it'll be closer, obviously, in this area probably than over here. Okay? So here's your job right now. Is what I'd like you to do is look at the masses of Y, ZR, NB, and MO, and they're all up here, or else if you have a periodic table, that might help you. Which average atomic mass reflects this mass spectroscopy the most? Like, that's literally how you have to read it. So which average mass, so here's Y, okay, here's ZR, here's NB, and here's MO. They're all right next to each other. So I have 88.9 to 95.96. Which one reflects, do you think, the average the most? All right, so figure it out. I'll give you 30 seconds to work with someone else next to you if you'd like. What do you think it is? And that's about the extent, by the way. Matthew Stafford. What do you think it is? ZR. Matthew Stafford said ZR. That's a franchise quarterback. That is right. It is ZR. Okay, the average atomic mass is 91.22. You got to take into account that it's 90. And this is pretty tight quarters, but if you kind of took the averages, it would really make sense. I hope for surely it can't be Y. I mean, some of you are talking about, get me to a 50-50 and I'll be good in a multiple choice. Can't be Y? Why? Is because it's the average is 80. There's no way to say it. The average is 89. Is below the scope, right? And then 95.96. It's way out here. That doesn't represent that at all. So right there, you're down to 2. So then you got between 93 and 91. Well, 93 and 91. I mean, it would make sense. That's not really a guess. You got the bulk of it all right here. That's right in the middle of these two. Okay. What if I asked you, follow-up question, how many isotopes exist for ZR? How many different isotopes? So for example, you say the mass. So like if it weighs 90, it's ZR 90. How many different isotopes are there? 1, 2, 3, 4, 5. That would be a follow-up. That could have been the answer instead. How many isotopes are present in this mass spectroscopy? There you go. There's 5. So that's how you read those. There's nothing more to it. So it's like, I don't know what I'm looking at. It's based on mass. You might have to identify what it is, or you might have to talk about the isotopes, or there's a couple other questions I will try to still find in some reviews and things like that, but that's where we're heading for that. Okay, jump down to the next thing. This is actually, if you weren't here yesterday, for a large group, we talked about, I was trying to show you how this works. Now, not every one of them is exactly the same, so I need to discuss this with you. Okay, so you see binding energy. One thing, let me show you. This is not specific in chemistry, it's just graphs. What is this signifying? There's a gap, right? Like there's a large space. Just don't get confused. It's not to scale. It's not a big deal. This says binding energy. All that means is how strongly the electron is bound to the atom. So the stronger the binding energy, the more energy it would take to remove that electron. Relative number of electrons. Yesterday, the example that we did, it was really nice and clean. It was 1, 2, 3, 4, 5. That was great. Sometimes it's not like that. Okay? Sometimes it's comparative. So right here, I only have 1, 2, 3 lines. Each peak, and if you want to write anything on here, be my guest, but you may have it already. Each peak is representing basically what I'd call a subshell or a sub-level. Okay? So we always start here. This is basically my nucleus. So this is representing, what did we talk about yesterday? That is representing the what? 1s. The 1s. I would label this underneath right now. I put 1s. This is 2s. And actually, if you want to label it all, this is actually 1s. And how do you know it's 1s and then a number? Well, because I have a lot of other electrons. So we're talking about the ground state. So this would be 1s2. Oh, so then each line is worth, in this one, 2 electrons. Okay? So this is 1s2, 2s2, 2p6, right? And then I jump. Oh, why does it jump? Well, because it's jumping to a new energy level. There is space. Even though energy levels aren't these actual spheres, there is a space in between of energy. This is just based on energy, but there is space of actual physical space as well. So then this is 3s2, what? 3p6, and then what do you think that is? It is a 4s2. And why is it not a 3d? Because 4s's are still closer than a 3d. They still go in order of distance when we place them. 3ds are actually technically further away. Yeah, but it's a 4 versus a 3. 4s's are closer than 3ds. 4s's are held tighter than a 3d. Okay, so well, it's 4s and then it'd be a 2. If it's in the middle of them, like if this was right here, that'd be a 3p5 as an example. Okay, so let's answer the question then. We got to figure out what this is, or somewhat. It says when two elements, they kind of confuse you on this problem a little bit, but when two elements combine to form an ionic compound, the sum of their charges is 0. For example, Mg2 plus and Cl minus form the neutral compound MgCl2. All they're saying is when you take two together, you crisscross them and you have a neutral charge. Element X will most likely form which of the following compounds? What element is this? Let's just label that first. What is this element? Not X, not X. It's C. Why do you know Ca? 4s2. So, what it's asking you right now is basically this. Is X going to combine with Ks and Mgs, or is X going to combine with Os and Cls? So first off, it's Ca. So the options are A, B, or CD. What's the answer there right away? CD, right? Because Ca would be a, Kevin, a cation or an anion. Ca. It'd be 2 plus.
Oh, plus a cat.
So it'd be in the front. So now, which one is it? C or D?
C.
It's C. And you know what? I got this right, but I had to reread it twice because they literally, I felt like they gave me the answer, which was confusing in the example. They're like Mg and Cl2, and then the answer is just like Mg. So I was like, what are they asking here? So that was what was confusing, but hope it makes sense. Ca with O would be CaO. Ca with Cl would be CaCl2. But I hope we understand why we know that that's Ca.
So, can you just go over the lines or whatever again?
Let's go over it on the next ones, because we get 2 more chances.
Wait,
Okay.
how do you know it's 4s2, not 4s1?
All right, we'll go over lines. Because this is full and I'm adding more electrons, that must be an S2. Again, it's relative numbers. The lines, you got to interpret, you got to figure out what the lines mean. Sometimes they mean 1, sometimes they mean 2. Sometimes there won't be any lines and you just have to look. Yes, that's usually
Just random lines everywhere.
Okay, so PS spectrum is photoelectron spectrum. It's what these are. I wrote that kind of in the title. Okay, so what I'd like you to do right now with you and a partner, I believe it actually asks an A. Write the electron configurations. You can write it below or write it on the side. What are the 2 electron configurations? What do I mean by that? The last one you just did would have been 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What are the electron configurations of element A and element B? Do that, please. If you want to work with someone else next to you, do it. But what are the electron configurations? And then identify them. So that's all letter A. What are the electron configurations and identify them? If we don't get through all this, I want to make sure that we get through A and B for sure. And then actually I'm going to jump to G. If we don't get to the other ones right now, we can. I would actually literally label it underneath, at least for your own sake. I would, and something like this, I don't know if that's okay. I think you probably need to do it all. And the reason why I say that, Camille, usually these kinds of things, they're smaller, so they're purposely not saying noble gas. If you, we never had that on the, oh, practice test we went over yesterday. So those of you that did not get to go over the practice test, we can somehow, if you'd like to, I can try to figure out a way to lend you stuff if you have time to grade. If you don't have time, then it's not going to matter. But what's element A? Silicon, yeah. Element B is chlorine. All right, this is a great example of this one. So again, the lines appear to be 2, 6, 4, and 6. So check this one out. It ends up in the middle. So that would make sense that it's a P5. So it's 1s2, 2s2, 2p6, 3s2, 3p5. So it falls in the line of the electron configuration. You need to understand those orders. The gaps usually signify a little bit of an energy space, but you can't always assume that. So just kind of keep thinking, because sometimes certain elements in certain areas, depending on the scale, and the binding energy, which is a fancy way of saying how hard the electrons are being held on or how tightly they're on there. It can affect that spacing. B, why do the 2s electrons have different energies for the 2 elements? Why do the 2s, right here, the 2s, so this is silicone, this is chlorine. So let's talk about that. What does this one mean? Is this easier or more difficult to remove these electrons than these, do you think? This is more difficult. Why is it more difficult to remove it from chlorine than, wait, am I mixing these up? Oh yeah, sorry, I got these mixed up. This is silicone? Okay. What's the nuclear charge? 14, nuclear charge, 17. It has a greater nuclear charge, so the electrons are being held tighter. Done. Whenever it's more difficult to remove something, nuclear charge. Every time. I'm sure there's a time that there isn't, but more or less every time. 50% of the time, it works every time. That doesn't even make sense. All right. Due to some time here, there's some very specific things I wanted to cover, and I wanted to jump all the way down to letter G. Okay? So please stay with me on this. So here, if they did a mass spec, what is a mass spec? What they did before. What I had before. With lines, with numbers. So what if I did a mass spec, and it has 5 lines? Okay? So this is not a mass spec. It was the one, your first one. You can look at yours. That has 5. That's not the same. For chlorine. 4 of the peaks correspond to 35, 37, 70, and 72. The 5th peak reflects a species with what mass? Okay, I want to go over this with you and see if this makes any sense at all. Where's 35 and 37? If you don't know this, 35 and 37, the average mass is 35.45. So you should interpret that as, oh, those are the single elements of chlorine, and those are the 2 isotopes, 35 and 37. Where does 70 and 72 come from? Cl2. But think about this. 70 is a product of what? 35 plus 35. What's 72 a product of?
37.
Maybe a 35 and a 37? So what would be the last peak? You have to predict. Think about the other things that are present. What would be the last number?
74.
74. Well, what? What's a 74 product of? A 37 and a 37. What happens to a mass spec again is that the atom is completely obliterated. You have ions, you have actual diatomics, and all the masses fall into play. So they have to give you a lot of info. But if they said there's one more, you got to just start looking at those numbers. Like, okay, those correspond to the single atomic chlorine. Those correspond to the diatomic. Oh wait, there's different masses of the diatomic. Oh, they're coming from the atomic chlorines at different masses. Oh, so 74 would make sense then. Okay, so that's kind of where some of that information could definitely be used. So we can work a little bit more on that as well, but I wanted to just show you to the extent that you would need to know about the electron spectroscopy.
Did you say that